All right. So thank you everyone for joining today's session. My name is Amit Dingare. I'm a director of data science at a company called Novelis. And today I'm going to talk about a case study on using machine learning in the aluminum industry. So before I start with my case study, let me actually share my screen. Okay. So before I start my case study, I'm going to talk a little bit about my employer. So my employer, Novelis, is world's leading manufacturer of flat-rolled aluminum products. What you see on the right-hand side is our end product that goes out of our factories, and then different parts are stamped out of it depending on the customer needs. We are world's largest recycler of aluminum. So one thing about aluminum, which I didn't know about before I joined this company, is aluminum theoretically is infinitely recyclable. So what we do is we buy a lot of the scrap, which includes used beverage cans, scrap from different manufacturing processes, and any other aluminum piece, and we actually melt it and create these sheets that you see on the right-hand top side. So this basically helps not only us to keep on churning out useful products out of this aluminum, but it also helps the environment. So my recommendation as a part of this talk is, if you get a chance, definitely use aluminum products, because there is a lot of environmental value coming out of those. In terms of our products, we supply those to four main segments: beverage cans, automotive, aerospace, and specialty products. What you see on the right-hand bottom are some of our end customers. So if you have drunk beverage in a can from one of these clients, there's a good chance that you have touched our aluminum or the automotives. So Novelis is a global company with a footprint in 9 countries. We have about 15,000 people that work in our factories, as well as in various support centers. And my team, the data science team, is also spread globally. We have presence in, at this point, 6 countries. So we started our journey into the area of data science about 2 years ago with the establishment of a digital center of excellence. And the idea behind this digital center of excellence was to bring digital technologies to solve complex business problems. To start with, we focus on operations for 2 reasons. One is operations is our bread and butter, and we can actually, any improvement we do has a much higher impact to our bottom line. And second is, in our operations, we capture a lot of data, which is very suitable for application of digital technologies. Just to give you an idea, we have these gigantic machine centers, which include right from melting to rolling. In each of our rolling centers, we have about 1,000+ signals being captured by sensors at literally very small intervals. So in some cases, it's like in some cases, it's minute. So if you think about big data in terms of data and the volume of data, we are literally a big data shop in every sense of the word. In our advanced analytics techniques, in our digital department, we use mainly 3 types of techniques. We use machine learning, we use linear and nonlinear optimization, and we use statistical modeling. Ours is an open source shop, so we are based on a Python stack. We use tools like Python, Spark, and cloud technologies within our center of excellence. But then within our plants, we use some of the off-the-shelf tools for generating quick value. So my team, which is at this point 7 people strong, has a dual mandate. We have to create value through use of data science and advanced analytics techniques in our operations, but we also have to build capability in our plants. And these 2 things go hand in hand for the sustainability end of this program. We can keep on generating of these techniques, but if we don't get adoption from the plants, this value won't sustain. So for us to keep that sustainable value, we have to find balance between both of those things. So each member of my team focuses on these two pillars. So how do we work within Novelis? As I mentioned, we capture a lot of data in our operations. Historically, this data has been stored in our plant databases, and very lately, about a year and a half ago, we started bringing this data to our cloud. But for many of our use cases, we typically start with the data that we have in the plant. We get that data, try to build descriptive analytics on that, try to build models through the usual process. And once we start seeing value from these models, then we work with our data engineering team to start bringing that data to our cloud data lake. And then we productionize our models in our cloud data lake. That model either in cloud or on the edge in our plants. And then the predictions made from these models are then available to the operators through various dashboards or various interfaces that they. So I'm going to talk about a case study that we did about 1.5 years ago in our remelt area. This was one of the very beneficial use case studies in that particular plant. It produced millions of dollars of value for that plant and helped us generate adoption of advanced analytics techniques within our operations. So I mentioned that we get aluminum scrap, we melt it, and then we create these sheets. So before we roll the sheets, we create different alloys from that. So we have these big melters. The picture that you see is one of our melters, where we take the molten aluminum and then may add alloying elements and create new alloys from it. So historically, what we used to do is we used to have a thermodynamic equation that used to predict how long it would take for the aluminum to reach the point of what we call being molten. And but that equation, I go in details later on, that equation wasn't performing correctly. So as a result, what used to happen is most of our batches used to go into this overcooked phase, right? Now that created two problems for us. One is not only it increased the process time, the actual molten used to happen much earlier than what the historical thermodynamic equation used to predict. So our process. And second is for us to move that molten to the next process, we have to bring it down to a certain temperature. So we had additional wait time as well. So that affected our throughput of the process. The second problem that we had was because the operators did not trust this particular model, they constantly kept on opening this main door. So you see what you see on the front, this is our main door. And they would take sample of the aluminum to see if the aluminum has molten. Now this created two problems. One is whenever you open that main door, a lot of the heat gets lost. And that creates a problem of like reduced fuel efficiency. But at the same time, you're talking about aluminum at 700 degrees Celsius plus. So when you take a sample of that, there is a safety hazard as a result, right? So we want to minimize this opening of the doors. And finally, it sort of like kept the operators occupied with things that are unnecessary. If the model was good, they could have used that time to do some other tasks. So we started this use case with the purpose of increasing the throughput of our remelt process by increasing the accuracy of our model that predicted the time to melt. And second was to avoid the heat loss as a result of frequent door opening. For this use case, we had three constraints. One is we had to apply models for 3 furnaces in this one plant. we couldn't change any of the physical infrastructure of the furnaces. Didn't want to put capex. We didn't want to make any major changes to our operating procedures. So our goal was to build a model that will accurately predict the time to melt. Now, when I say time to melt, I think our job, at least my team's job, was to predict of heat required to melt for that given alloy. And then we had a static equation that would take that amount of BTU into and convert that into time scale. So the end target of our model was to predict how much heat was required in terms of BTUs to be added to melt this aluminum. So before I go into the actual model, let me talk about the process we went through to develop this model. So originally we had a thermodynamic equation that used to do the job of predicting the time to melt. This particular equation had two main issues. One, it was constant equation for all the alloys. And second, this equation was purely based on the weight of the molten. And if you know thermodynamics, the surface area is equally important than as the weight of the molten. So the first thing that we did is we modified this thermodynamic equation. So instead of having one equation for all the alloys, we created separate equations based on different latent heat of fusion, melting points for different alloys, and surface area as a parameter in this equation. So as a result, we were able to cut down the total melting time by about 3%. The next iteration was, we thought, okay, we'll build a complete which will replace this thermodynamic equation. This model performed relatively well, but in terms of its predictions, we had a high variance. And this was not acceptable from a planning perspective. So as a last stage, what we did is we combined the earlier two phases. So we took the modified thermodynamic equation and we took the machine learning model, combined those two, and created a model where the base prediction was coming from the thermodynamic equation, but then we had several features to capture the noise of the process. And this turned out to be a very successful model. We were able to cut down the total melting time by about 12%. And 12% in every batch, if you add up over a period of year, it's millions of dollars. So this is how we built our model. I just want to make sure that we have time. Took data from our OSI PI system. If you are from manufacturing, you probably know what that is. We took data from the remelt database where we keep all the event-specific information. We combined those two in a database and generated features. So to start with, we had 118 features. And I mentioned that in the past, we used to go into this overcooking phase. So to adjust the target function such that we teach the model what normal operations would look like, what normal BTU would look like. So we use extrapolation to adjust the target function. And finally, we had a pretty successful model. So I want to highlight 2 points. One is the feature importance, and other is the R-square. If you're from any other industry, you might find this particular R-square pretty high. But one thing you have to keep in mind is look at the feature importance. The topmost feature is the theoretical equation, and that's contributing 50% of the model weight. And that's one of the reasons why we have such a high accuracy. So 50% came from the thermodynamic equation, and various other features such as the events that happened contributed for the remaining feature importance. So in terms of the model deployment, we originally wanted to deploy this model in our cloud, but given the constraints around the timing and bandwidth and various other reasons, we decided to deploy this model in our plant on the edge. So we deployed this model as a RESTful API. So how this model works is we have these two systems, OS and the remelt database. They send data to this common layer. We call it automation interface layer That's where the feature engineering happens. Once those features are created, we call the API every 3 minutes, passing the features as a JSON. Then we get the predictions. Predictions are sent back to AIL. On AIL, so we are predicting the amount of heat to be added. And then AIL converts the heat to time. So once that conversion happens, AIL sends that information to our one user interface. And this is the interface on the machine that operators can see. So there are two things that are shown. One is the amount of heat required on the top. So show them the total melt time. So now this actually frees up the operator, because they don't need to keep, if they trust the model, they don't need to keep looking, waiting for the batch to complete. They can go and do other tasks. So given this model, we have actually been able to generate a value of about, I won't go into the actual numbers, but millions of dollars. And one of the very successful models in one plant. So right now what we are doing is taking this one model and replicating to other plants of Novelis. So I want to end with some key takeaways. Metal manufacturing is a very interesting industry. I worked in various other industries before coming to this one. And if you think about big data, it's a big data industry in every sense of the word. Large dimensionality as well as pretty high volume. Industry historically focused on Six Sigma, moving from those areas to more nonlinear modeling using machine learning. One of the important things that my team has learned in this last 2 years is we cannot ignore the basic sciences. So physics and thermodynamics are pretty good. When you build your model on top of that, you can actually generate the best models. And in the advanced analytics is turning out to be a very big value driver. And for us to sustain this value building capability within our is quite essential. So when those two things come together, we can actually produce a lot of value. There are a lot of pretty interesting problems to be solved, and my team is currently working on solving those problems. So to end my presentation, thank you very much for your time. If you have any questions, please reach out to me at the email address.